Ah, finally. Let me first check if everything is being recorded, actually. Okay. Okay, that should be good. Okay, terribly sorry about this delay. I'm always having trouble with these devices. It's not my favorite thing. Actually, I got it started, so let's still with a 10-minute delay. Incredible. Are there any questions about yesterday? Okay. About remote procedure calls? Yeah. Yes. Why RPC is not a good example for access transparency? Well, you'll get the answer to that question when we get to discuss RPC. Don't worry. Okay? Any other questions? Yes?
Yeah, I was wondering about, could you give a definition, difference between grid computing and cloud computing?
That's a tough one. I think I said yesterday that I don't like giving definitions at all. If you want to talk about the difference between the two, grid computing is generally associated with high performance computing, and cloud computing is a successor to grid computing, where they actually provide compute and storage and network facilities available for remote processing. So I would argue that cloud computing is moving your servers from here to there, and grid computing is making stuff that is already available at different sites available to you. Is that a big difference? Yes, it is. Such is life. Okay, so it's very difficult to give a very precise definition of either one, actually.
Could you argue that cloud has more to do with the direct end user and grid computing has more to do with organizations?
No, you cannot. Most organizations are thinking of putting stuff into the cloud, and most end users are not even aware that they're doing anything in the cloud. Okay? Okay. Any other questions? Okay. I have registered at the moment about 62 emails. I think there are more people in this room. Some of you did not get an email back. How do I know? Because I got a message delivery failure of some people. So if you didn't get an email back, that means that you have not been registered. And I encourage everyone to enroll, because then I can send messages out saying, hey, there's a video out there. Okay? Now there's one thing about this program that I'm using, is that it's using its own codec to actually compress the files. I've been paying a bit of attention to that, and I haven't found a decent codec that is universally applicable, but that actually seriously compresses the file. So at least for those people who are running Windows, they should be able to use this. And what I will do, is actually transfer all the AV files to an MPEG-4, and then the problem should be gone. Okay, but I haven't come to that yet. Okay, let's continue with not getting that message again. I want to continue with talking a bit about architectures. This class and tomorrow will be about architectures, and then tomorrow we'll also start with chapter 3. What I want to discuss is architectural styles, where they come from. And the architectural styles actually tell you a lot about how many modern distributed systems are organized. And they do this to try to master complexity. Okay? Here are two organizations that many of you actually know. Let's first take a look at this one over here. Let me see if I can get this thing to work. It's the layered architecture. And the idea behind the layered architecture is that you split your system into different layers, such that a higher level layer makes use of the services of the layer just beneath it. So then you can have a request flow that goes from the top to the bottom, and the response flow from the bottom to the top. The layered style is used in many client server systems, okay? But also somewhere else. I don't know what's going on here. You all know this. What's the canonical example for layered style?
OSI model.
The OSI model, exactly. With its 7 layers, or actually, you know, it goes beyond that. There are people who've been thinking of what to do with the application layer. Okay, but in networking, and be it the OSI model or the modified internet model, they have a fairly strict stack of layers, and indeed the flow is really from the top to the bottom and from the bottom to the top. Virtually no exceptions. Okay? What could typically be an exception, actually? And a useful one? Can you come on? I actually gave a hint of this yesterday.
Well, in case of the OSI model, if you put on top some, for instance, on UDP, you want to do some call checking or latency checking, stuff like that. Usually done by TCP. You would skip that layer and do it yourself on a different layer. For instance, on an application layer.
Yeah, that could be one. Actually, I've noticed that this whole thing is not interesting because it was recording stuff. There's an easier example. No. Oh no, even easier than that. Callback mechanism. You know what a callback is? You send something out there, and then suddenly you get a callback. Someone will be calling you as the reaction to something that you set up there. So you see this in operating systems, for example. When you register a function with the operating system, and what the operating system will do at a certain time, it will call one of your handles. Okay? Watch out what's happened here. The operating system is calling you. You could argue that this is a form of violating the layer. But like I explained yesterday, you could also say, no, this is completely okay. I mean, there will be an up call, but is it violating this layered structure?
I can't see why, because you're still using the layer, right?
Yes, but it's not a response that you're sending back, or is it? That's the interesting one. So the operating system is just doing what it's told. So it's not making use of the services on top of it. That would be the argument. It's doing something, is actually offering a service to the higher layer by means of a call. That's a subtle issue. Okay? So again, this is another example where you could go either way in your reasoning, and it's not yes or no, it's the reasoning that's really important. Okay, this one most of you actually also know, object-based systems, and the whole idea is that you organize a distributed system in terms of objects, and that these objects call each other. Okay? It's actually a very well-known method, and instead of talking about objects, you could also talk about programs. Objects can be small, but they can also be entire programs. It's also a well-known architectural style for distributed systems. And what happens in many of these systems is that you actually place objects on different machines. Or perhaps two objects on the same machine, but your unit of distribution is the object. Am I making any sense to you guys? Okay? And I also just gave a very good reason why you would want to follow an object-based style, because it will give you a natural way of distributing your stuff across multiple machines. And that's what distributed systems is all about. I'm not saying that it's necessarily a good way. Okay? Now, here's work for me. Yes. Here are two.
Sorry.
Hmm?
I have a question.
Yes.
What would be a natural way of distributing things in a layered architecture? If each you put a separate layer on different machines, or
What happens is that people place layers on different machines. And yes, that's actually, you can ask yourself, is that actually a good way to distribute things? And the answer again is yes and no. I'll come back to application layering in just a minute. There are the traditional 3 layers. And there are good and bad reasons for following that distribution. Yes?
What you said from previous lecture, is it for example logic system there?
Sorry, I didn't understand.
In the previous lecture, it was, I don't recall exactly, but it was about some kind of master server which could make logic machines.
Was that in the server clusters where you had a, oh, wait a minute. In cluster computing, where you had a master node?
Yes.
Yes, okay. Whoa, that's a good question. Is the combination of a master node with a bunch of these compute nodes, fits that one of these architectural styles? That's basically your question, I guess.
Yes, that better.
Okay. Let's vote. I always pull this trick out. Okay, who votes? I won't vote. I won't vote. Who votes that this is a layered approach? Everyone has to vote. So if these are the hands for the layered approach, that means I want to see lots of hands for the object. Who says that this is an object,
I
please?
say it's hybrids because.
Oh, hold on. So first, okay, you'll get a chance, okay? The single one say no.
What if you don't have an opinion, guys?
Ah, sorry. No. You're a master student. You gotta have an opinion. No. Beyond that phase,
That's the fallacy right there.
What?
That's the fallacy right there.
I know, but you gotta go for it. No, I will not accept that you guys don't have an opinion. I don't care whether it's a wrong opinion, but you have reached the level that you just gotta have an opinion. Okay? At least in my class. So let's see the object hands. Okay, that's more than the layered hands. Okay? And some people just don't know or don't want to have an opinion. Okay. So you argued that it was hybrid.
Yeah, the master node to the compute nodes is layered, but the compute nodes themselves are no object.
Okay. Any other thoughts on this?
I think it depends if the compute nodes communicate with each other. If they don't, yeah, I think it's very clearly layered. You can have the master layer on top of the slave nodes, slave layer, and all that. If they do communicate, I think that's what's right for hybrid.
Okay.
Good for you.
Well, I don't know. I don't know what the architecture would be. You could argue that it's layered under the assumption that the master node actually receives all the requests and also the request to get the work done. Okay? And what it does, it makes use of the services offered by the compute nodes, and it gathers all the results. And then in that case, yes, it would be layered. But for the same reason, you could say it's object-based, because what I did was I distributed the work among the different compute nodes, and even independent of whether they talk to each other or not. I think your argument is strong, because then there will be more obviously than there is an object-based approach. But if these compute nodes do different things, and you've programmed that way, then you could say, well, this is just an ideal distribution of my program. Now, the reason why I find it a bit difficult to talk about that specific example as fitting into this architecture was that it's an example about machines. Okay? And these architectures are actually about not necessarily the machine, but the organization of your distributed system as a program. So it has much more to do with the logic of your distributed system than who's actually doing what on a specific machine.
Does this mean we're talking about middleware then?
Yes.
Yeah.
Distributed system is middleware.
Yeah, but these models.
Okay, that's a good question. Yeah, in principle, yes, I'm talking about the middleware. But there will be numerous examples throughout the whole course where the distinction between the machine, low-level system stuff, and perhaps specific middleware is sometimes difficult to make. Okay? Most important about this discussion is not the answer, but the reason. Okay? Now, these two architectures, the publish-subscribe architecture and the shared data space architecture, are actually very important. What they try to do is to decouple processes. So an observation is that in very large distributed systems, you are dealing with the fact that they become intricate because the processes know each other so well. And by knowing each other so well, I mean they know exactly to which other, one process knows exactly to which other process it should send a message. And exactly means either its process ID, in what form ever, or actually an IP address. Now, as soon as you have that, and let's take the IP address as an example. As soon as you have that, your system becomes a lot more difficult to actually configure or change when it's needed. For example, because you're migrating to different machines. And if that means you have to change IP addresses, hey, you got yourself a management problem. Now, what people have been looking for is, can we organize the middleware in such a way that processes actually don't need to know each other? And they're trying to look for architectures that will allow processes to be decoupled in time or decoupled in space. And decoupling in space is actually referential decoupling. Okay? Now, what does decoupled in time mean? It means that when you send a message to its destination, the sender and the receiver don't have to be online at the same time. They don't have to be active at the same time. A simpler one is where you have a decoupling in space. I will send a message, but I don't know exactly who's going to receive it. But that's not my concern. And in a publish-subscribe system, in a simple publish-subscribe system, what you do is you say, hey, this message is about X. And you attach a label or a tag to your message, okay? And that message is then sent off in the distributed system. And so-called subscribers, now the recipients of that message, they have subscribed to messages tagged X. Okay? And then it's the job of the distributed system to make sure that messages tagged with X are actually delivered to the subscribers who wanted to have messages tagged with X. And that's a decoupling in space. And what you're seeing over here on the left-hand side is this publish-subscribe system with processes, components, decoupled in space. Referential decoupling. So you can actually have a component over here, a process, for example, who publishes stuff, and technically that means that it puts it on an event bus. That's your middleware. And the middleware has the responsibility of gathering subscriptions beforehand and making sure that that message is then delivered to the subscribers of that message. That's a decoupling in space. The publisher doesn't know where that message will eventually go. If you also want to have a decoupling in time, then you're saying that I don't know where my subscribers are, but I also don't know when they're up and running. So what I can only do is make sure that my messages get dumped in a shared data space, and when a subscriber gets online, that message is actually removed from that shared data space, or copied from that shared data space. Who has ever heard about Lynda, or Java Spaces, or Genie? Let me see some hands. Okay, a few. What I just described with a shared data space is Java Spaces, Genie, or Lynda. Okay, in Lynda they have tuple spaces, and I have an example in the book how that actually works. In practice, what you see is not this system, not the decoupling in time and space, but mostly this one. And there's actually a reason for that. Can you imagine what that reason could be? Well, actually, it's no, wait a minute. I'm sorry. I'm now asking the wrong question. A good question, but at the wrong time. What makes these schemes and then also these schemes difficult to implement? Where do you see the problem?
With the second one, I'm asking myself how much save data in the shared space.
Okay, so there's a question with the shared data space. How long should you save data? But that's a good observation.
I think the problem is for the middleware that for example, just to specific your message, it doesn't know that who is the receiver and it's forced to search a lot and to find the, for example, who is linked to the center of the program.
Okay, so summarizing your observation, the matching itself can be difficult, which is a true observation. So the problem that both these architectures have is that you can say that your message has tag X, but how do you make sure that you can actually match to exactly the subscribers of X? And the easiest way to do that is by means of a centralized implementation. Okay, so you have another server says, just give me all these subscriptions and whatnot. I'll do the tagging. This leads to a message broker, as it's called, and then I will forward the messages exactly to the subscribers. Okay? And if you don't want to have a centralized implementation, what then? Now I'm already anticipating a number of slides that I'll be discussing in just a minute. Yes?
You run into problems with synchronization. People send a message first before the other. Centralized.
No, that turns out not to be a problem. But I'm not going to explain that right now. You know, you could just have tough luck. If you're late with your subscription, hey, tough luck. It'll be a policy decision. Yes?
I think it's very difficult to also decouple middleware in space.
Also decouple the middlewares.
Right.
Explain.
What you're trying to do is to make sure that the components don't have to know where the other components are. So you have a middleware to receive messages and send them to the right component. But if you distribute the middleware over different machines, then the middleware will have to correspond with each other, and you will need to know.
Okay.
Right? I mean,
Okay.
You need another middleware to decouple the middleware.
Okay.
That is perfect.
So the observation here is that if you go to this decoupling, then you also need a decoupling mechanism for the middleware. Yes and no. Yes, if you make, I will call it a mistake in your reasoning, that middleware is something that runs on a single machine. Okay? This is an important way of thinking. You got to get rid of it. What I mean by that is middleware is a piece of software that, of course, runs on a specific machine. But the way to look at distributed systems and the middleware is that you have a bunch of collaborating machines. So it's really like a distributed operating system. Okay? It lives by the fact that there are other parts of that same system that are residing on other machines and that to a certain extent may or may not know about each other, but your assumption is they all collaborate to building this, to hiding the distribution aspects. So that's the mistake in your reasoning. Otherwise you will be right. And the right part, let me then formulate it for a distributed system, is that if you want to decouple, not necessarily also space, but if you want to get rid of the centralized component, you have to find a way of making sure that you still know who will do the matching for you. So you need a way of distributing the matchers, so to say. And there are ways to do this. These things are called distributed hash tables. And I will be coming to distributed hash tables in just a minute. Okay? Any other questions? Good. let me move on. Okay, an important, hold it, just realize something. I'm sorry about that. Okay, I want to switch to something else. Very, very important, the client-server model. It's a very simple idea. Your whole distributed system is organized as a collection of machines, and I'll just keep it simple. A machine is either a client or a server. And the whole idea is you put services on servers, and you have clients access services to get the stuff done. And the reason why this model is here is because we're so used to it. And when I come to explaining remote procedure calls, you'll see there's a one-to-one mapping with remote procedure calls to this model. And it's very simple. You have a client, which is just a program doing things. Here it goes. It's over there. Whoops. This one is over there. Okay? It needs to get something done, so it sends a request to a server, and it waits. It blocks. The server does its job, sends a response back, client is happy, and continues where it left off. Now, people have been saying that the client-server model is old-fashioned, it will go away, and it's virtually dead. Not true. The client-server model is so extremely simple that it's here to stay. Okay? One thing that you'll notice when you develop distributed systems is that it is literally extremely simple to come up with a complicated solution, but it's actually very difficult to come up with a simple solution. By the way, this is a general rule of science. I encourage you, certainly with computer science, to try to apply the second rule. Pay a lot of effort to come up with something simple. A complicated solution is an easy thing to invent. Okay? And for its simplicity, my claim is it will survive. And even when you talk about peer-to-peer systems, what you'll just notice is that a program will sometimes play the role of client and will then sometimes play the role of server. So the way of thinking is actually very convenient. Okay. Now, so it's important to realize that they follow this strict request-reply model when it comes to using services. Now, coming back to your question about layering. So let's focus on application layering. And what is a very common scheme? The common scheme is to use 3 different layers. Okay? And this is a scheme that has been widely applied to distributed systems and notably to the organization of sites. So you have a user interface layer, and in many cases the user interface layer is replaced by something like a control layer. That's all fine. So you don't necessarily have to have a real user interface. Then you have a processing layer, and you have a data layer. The user layer is often relatively simple unless you have a really fancy user interface, but basically it's a kind of a control layer. The processing layer is where you burn CPU cycles, and the data layer is where you store and retrieve your data. Okay? And the interesting observation is that this layering has found its way in many distributed information systems. And when you think about this, it's actually kind of weird. It's weird in the sense that this is a logical layering. So if you would organize any non-distributed program, you will probably follow this layering as well. And what I've always been surprised of is the fact that as soon as people started to thinking about distributed systems and say, hey, we have this 3-layered approach, let's just implement different layers on different machines. So you have your database layer, meaning you have database servers, you have application servers, and you either have something like web browsers, or in the case of websites, you have your Apache server as your entry point. Okay. And to make this clear, this is Google, but not really, of course. But if you think in terms of search engines, you can easily apply this 3-layered approach. So you have your user interface over there. Then what you do is you type in your browser all kinds of keywords. What happens is you actually get a keyword expression, and then you have a query generator that takes these keywords and then operates, let's say, on a relational database. And the relational database is indeed logically placed at the data level. It just spews out a lot of web pages. Then you have your ranking algorithm to at least try to order the responses and then send it back to the user. Now, there are all kinds of variations on this theme. One of the most important ones is that if this would be Google, it would not have a single database standalone, let alone a single processing layer. Now, I always ask every year this question: how many servers do you think Google has? How many? I can be more accurate. How many servers do you think Google had in 2006? Because it was 2007, I think. That's at least the number that I know. Give me numbers. 200,000? If you were a distributed system developer, okay, which you are by now, okay, what would you think would be a reasonable number? So I'm asking you to do a bit more than just guessing.
Put it in Amazon.
Put it in Amazon.
How many servers?
Now, in total, how many servers does Google have?
In total for all the services?
For all the services. I'm just making, of course they have many different services. Oh, I can say a bit about that in just a minute. But I wanted to see if you guys have an idea of how big Google could be. So we're talking 2006. How many servers, machines would Google have? What would you think is a reasonable number? A few million.
Wikipedia is 10,000 and they try to be small, so that's why.
How many servers do you think Wikipedia has? How many?
10,000.
No, 400. So Wikipedia has 400 servers. I think that was 400, maybe 600, I don't know. So how many does Google have? Well, how many did Google have in 2006 or 7? 500,000. 500,000. 450,000 was the estimate. I wouldn't. Do I dare give an estimate? I don't know. It's probably now in the millions. Is it a lot? Yeah, it's a lot. Can it be managed? Yes, it can. That's what they do, right? So it's doable. So it's a good example. And I have to say one thing. Of course, not all these million servers are being used at the same time to run Google. Okay, that's also obvious. I have no idea how many servers they actually use for the Google search engines, but it's obvious that we're talking about thousands, maybe tens, maybe hundreds, thousands of servers. It should be something like that. Now, the interesting thing about this example is they do form a distributed system. And, I don't know exactly how Google does these things, but Amazon, for every small thing that you see on that screen, they have a different service, okay? So before you actually get your Amazon page in your web browser, tens of services have been invoked for you. And many of these services, they follow this three-layered approach. So what you'll notice, if you could dive into the organization of Amazon, is that your request will follow a client-server approach, will hit web services that go to database services, and collectively they manage to get this nice page for you up and running. Okay? Just to give you the impression that it can actually work. Okay. Yes. Let me see. Okay, yeah, let's do this as the last slide before we take a break. Now, what I just said is that you can make a distinction between the logical level and the actual mapping of your layers. Okay, so I'm talking about 3 layers, but in principle, you could take these 2 layers and map them onto 2 machines. And this is what lots of people have been doing. And then we're generally talking about multi-tiered architecture. So the tier is then more focused on the actual machinery. And here you see a number of combinations of mapping the different layers onto different machines. And here on the left-hand side, you see a really old-fashioned mapping, which you had when you had these green CRT terminals. I think this is way before you guys were even born. But they were used mainly with mainframe computers, banking situations, and also flight reservations, these type of things. And basically what it boiled down to is that you had a very simple interface, and everything was running on the mainframe computer. And maybe there were multiple mainframe computers, but that doesn't matter. Everything was there on a server. Then gradually, people started to move stuff to the client side, to the client machine, I should say. Okay? So here you have a more advanced interface. A typical example here would be the X interface for X system for people familiar with Unix. Well, actually, not even Unix. Your Android smartphone also has this type of stuff up and running. So basically, what you do is you put lots of stuff on the client machinery and most of the control of the interface as well. And then you talk from your machine to applications on a server. Okay? And the applications, they also ask the screen what they should do. And in X terminology, we'll come to that later, in X terminology, the application now has become the client, and your screen has become the server, because the application is talking to the screen. That's a minor detail, we'll get into that later on. Now, that trend continued up until, this is probably the 80s and the 90s, and this is where we are right now. No, this is where we were a couple of years ago. By more and more moving stuff to the client machine, until you actually had this configuration. Everything was there, okay? Even part of the database. My example for that situation is the situation where a couple of years ago you would get from your bank a CD which would allow you to install a complete banking application. Okay, so this thing had caching information and whatnot, and then once you did your stuff, it actually contacted the bank and did the transfer. And the actual transfer, of course, took place at the database on the server side. Now, these things are called, where is this? Yep, this thing is called a thin client. Actually, that is a thin client, and this thing is called a fat client. And we're moving back again. Okay? So there was, once we were over here, there was a strong trend back towards this thing over here. And I'm sorry, I'm having fights with this thing. I just don't know how these interfaces work. I'm used to consoles. I'm not used to advanced things like this. Why would we move back from fat clients to thinner clients? What? For? For portability. Tell me more.
Yeah, I think like you can like use our application on many different devices. You don't have to install it. It's like a simple application like web browser, and you can use it from
Yeah, it's coming very, very close to. If you would give this answer on an exam, you would get, let's say, 9 out of the 10 points, something like that. So it's the core is okay, but I think you could formulate it just a bit better. Yes.
Cutting costs, because you can easily sell many cheap devices to a lot of customers who can use all kind of complex servers that are running in the services that are running in the cloud.
Well, strictly speaking, I guess you're right. So there's a cost element, but then if I take a look at what Google is doing with their devices and Google Chrome, the devices are still kind of expensive, okay? And they put Google Chrome on that, saying, "Hey, don't do anything there. Come to us." But strictly speaking, you're right. Yes.
My argument would be quite simple, maybe or maybe wrong, but if the client is doing more job, then why to use server? Like in the case of fat client is doing most of the job.
Uh-huh.
If we have servers, why not to make use?
Okay, but that will be a performance reason. So, why would you let the client do so much work? Well, because it offloads the work of the server.
Balance the load between server and client. So let's get little back. Not so thin, not so flat. But client is doing some job.
Okay, but if you would have fat clients that can do that processing, it will be okay. Okay, but so in general your argument will be okay, but this was a general trend, even from very powerful clients like PCs. Yes. Oh, hold it. Sorry, he was okay. Yeah, you go ahead, and then okay.
Because nowadays everything's about data harvesting, so getting the since information is power, getting the information, the power back to, for example, Google makes sense. So to go back to the same.
Yeah, okay. So that's an argument where where you really can't offload anything to the client. Just don't do it. That will be a good reason. But there's actually another one.
Because generally speaking, you need multiple implementations of program which run from the client side and the one which runs from the server side.
So that was the portability argument, indeed. Okay. But generalize on the portability. Yes. Yes. That's the key word here.
Yeah, because if you're as a server, you're more in control of your application. So you get a small piece of the application to the client, and then
So on the left-hand side, you don't have help desks. On the right-hand side, you have lots of help desks. Okay, because on the right-hand side, you have your customers, and customers are not techie. Okay, they really don't understand. And to be honest, even if you're a techie customer, you say, what the fuck is going on over here? And then you just, I have this from time to time. What is going on? And then you still have to phone the help desk. But if you move to the left, the functionality of the help desk will be less. And basically it boils down to a manageability problem, which includes portability. Okay, that's part of the management problem. But now we're moving a bit back to the right. Why is that? And you know the answer. You just have to say this keyword again. Manageability. Why? Because we now understand how we can do remote manageability. And one of the key elements here is web browser technology. Because what you do is you go to a site, you log in whatever, and what you get is the applet or the scripting code or whatever that will actually do the work that is supposed to be done on your machine. And if there was a bug in that thing or something was wrong, hey, that doesn't matter. It will be instantly fixed. And the next time you access that page, by a simple reload, hey, you get your thing again. So the manageability is exactly the same reason why we can move back again, because we can do remote manageability. Not in all cases, but that actually shows you how these trends can go back and forth. Yes?
So basically what we drafted last time is point F, which is not on the slides.
The standalone computer? Or
yeah, well, basically the networks, the distributed network, you had the example with the building, with all these sensors that have their own interfaces talking to
okay.
each other. Would that be like F and that?
Oh, this is a very good question. Thank you. So what happens if the database is gone as well from the server? That's basically your observation. And I agree, that would be point F. You could argue that that is a fully decentralized distributed system where all the functionality in terms of three layers is placed on every machine, a completely symmetric case. Indeed, I didn't draw that actually here. Actually, you just give me inspiration that I should do this for the third edition.
Because of the policies and rights to see that data. No, but yeah.
You're out. Sure. I mean, there are all. Okay, just a minute. There are all kinds of things why you can't go to F. That's true. But strictly speaking, in this scheme, you can go to F. Okay? Now, before we take the break, anytime I ask a question and you don't know initially what the answer would be. Why would you do X and not Y? The general answer is always security. Okay? Always. And you'll notice, just do this as a kind of a thought experiment. Every question that I ask you, so can I answer with security? In 9 out of 10 cases you can. Of course, you have to explain why it will be a security issue. And in this case, your answer would be, okay, you say, you can't do this because of security reasons, because how do you actually control access, authorization? And you would have to have other architectures to make sure that can be done, but security is generally a good answer. But I like your observation. I think it's very, very good. Thank you. Yes?
Why not go all the way to A then?
Why not? That's actually also a good question. Why not all the way back to A? You know the answer, by the way. Yes?
Are we going actually all the way back to A with all that cloud stuff? You just log in, you access all your data somewhere without
why would a cloud be different from this scheme? And actually, I cannot answer your observation with yes, you're right, no, you're wrong, because, for many reasons, actually. So the observation is here, aren't we moving to A because of cloud computing? Everything is out there in the cloud, and what you get is a simple web browser and access things. Okay, let's hear some voices on this, yes?
In that case, your browser is still your application, or you need an application for protocols.
Exactly. So you would, in this modeling of things, you would still be more on the right-hand side because you deliberately put some stuff at the browser for a number of reasons. One reason could be user experience. Okay, I get really nice performance and gadgets and whatnot. People appreciate that. Yes.
There are actually approaches to go totally back to A. This TV stuff, and I think there's a startup that is trying to kind of do all the computation on the server for playing video games, and then have only the visual data transported to the client, so you can start to play video games with your TV. But in fact, this cuts with two important parts we had in the last lecture: latency and bandwidth.
Yes. And you also know a very good example where you can see how yes, thank you. So who is using remote desktops? Okay. A remote desktop is A. Okay? And you instantly see what you get with a remote desktop. Those who have never used a remote desktop, you know what I just said. You have to go home and use a remote desktop. Thank you very much. That was the implicit thing, okay? Be aware of these things. But then you're at A. And then what you'll notice is that you'll be bumping into performance problems, depending on where you are, okay? If you do this in your own house, well, it's not too bad. If you do this Windows on a Linux machine, whoa, something's fishy's going on. If you have Windows machines in the house using remote desktops, I'm always flabbergasted. If my Linux client is talking to a Windows machine with remote desktop, I'm still happy. But as soon as I go over a normal, really remote link, like a wide area network, or I sit at home and I get access to the view, bad performance for the reasons that you mentioned. Okay, let's stop here and take a break then. A 10-minute break? Okay.